So our next relative of f of x is 2 times f of x. And we're going to create a table of values, see what happens to the graph. Any conjectures before we start making our table of values? What do you think is going to happen to the graph? It's going to change the x-intercept? Okay, yeah, the x-intercept is going to stay the same, but everything else is going to change, or? And gets stretched, yeah, gets stretched. Because f of x is just y, right? That's a fancy name for y. So this says 2 times y. So you can take every y coordinate and double it. So when I make x -4, this is going to be 2 times f of -4. F of -4 is 2, so this is 2 times 2, which is 4. And I'm going to keep getting 4s for all of these, because the y coordinates of the original graph are all 2. And double them, I get 4. And then when x is 1, I'm going to do 2 times f of 1. And f of 1 is 1. So this is 2 times 1, which is 2. And then 2 times f of 2. F of 2 is 0, so I have 2 times 0, which is 0. And now I have 2 times f of 3, which is 2 times -1, which is -2. And 4 times f of 4, which is, oh, no, sorry, 2 times f of 4. 2 times f of 4. F of 4 is -2, so this is 2 times -2, which is -4. So I go to my graph, and I plot my points where these are my x's, these are my y's. So I've got -4, 4, -3, 4, -2, 4, -1, 4, and 0, 4. And then I have 1, 2, 2, 0, 3, -2, and 4, -4. So there's my new graph. This one, my green one, is y equals 2 times f of x. And the one in black is just y equals f of x. So how would you describe the transformation that took place? How could you take the graph of f of x and transform it into the graph of 2 f of x? How are those two pictures related to each other? X-intercept is the same. Yep, and that will always be true because x-intercepts have y coordinates of 0. So when you multiply something 0 by something, it's going to stay 0. So the x-intercept will stay the same, and everything else got vertically stretched. So 2 f of x is a vertical stretch of f of x. Vertically stretched it. And that's going to be true anytime you multiply f of x by something that's bigger than 1, right? Because when you multiply, you have to multiply by something bigger than 1 to get a bigger answer. If you multiplied by a fraction, something between 0 and 1, that would squish your graph. It would make all your y coordinates smaller. We'll do an example of that in a second. So in general, if you multiply f of x times some number k that's bigger than 1, we get a vertical stretch. k times f of x is a vertical stretch of f of x by a factor of k, because we're multiplying by k, so we use the word factor. Vertical stretch by a factor of k. As long as k is bigger than 1, this is a stretch. Okay, so I want you to try one. Here's a picture of the absolute value of x. I want you to make a table of values, draw a sketch, and give the equation, right, of 3 times k of x. So we're going to do 3 times k of x, so that means 3 times k of -4, because -4 is in the x column. That's 3 times the absolute value of -4, which is 12. So basically, we're going to take the absolute value of x, then triple it. So this one's going to be 9. This one's going to be 6, 3, 0. Absolute value of 1 is 1. Triple it and you get 3, 6, 9, 12, 15. So when I plot these points, I get -4, 12, -3, 9, -2, 6, -1, 3, 0, 0. X-intercept always stays the same. 1, 3, 2, 6, 3, 9, and 4, 12. Connect them. And I got my vertical stretch. It's like I just grabbed onto the ends of my function and pulled upwards. Okay. And its equation, this one is y equals the absolute value of x, or k of x equals the absolute value of x. This one is y equals 3 times the absolute value of x. All right, next relative. Now I'm multiplying, still on the outside. I'm still on the outside, and I'm still using multiplication, but I'm just changing the value I'm multiplying by. Instead of multiplying by 2 or by 3, like in the last two examples, I'm multiplying by a half. So if I multiply all my y values by a half, I would expect them to get smaller, right, instead of bigger. So let's just double check that that's what happens. So I want 1/2 f of -4, right? And f of -4 is 2, so I want half of 2, which is 1. I'm going to get 1 for all these. And then I want half times f of 1. Half times 1 is a half. 1/2 times f of 2. That's a half times 0. Just 0. 1/2 times f of 3. That's 1/2 times -1, which is -1/2. And 1/2 times f of 4, which is 1/2 times -2, which is -1. So I plot each of those. I've got -4, 1. All of these are 1s. And then 1/2, 2, 0. 3, -1/2. Oops. 3, -1/2. And 4, -1. So this time, multiplying by something on the outside, it still caused a vertical change, but it caused a vertical compression or a vertical shrink. Okay, so if you multiply on the outside by a number, by a fraction, you end up shrinking your graph vertically. So in this case, 1/2 f of x is a vertical compression of f of x by a factor of 1/2. So you can see what happens with the factors, because if you look at the original graph, what was its range? What was the range of my original f of x? The y value is where it lives. -2 to 2. And then what's the range of my compressed graph, my relative? -1 to 1. So my range shrunk by a factor of 1/2, right? My range is half of what it used to be. So that's another way to check or figure out what your factor is. Look at what happens to the range. In general, when you multiply a function outside by k, if that k is a fraction, like between 0 and 1, like 1/2 or 1/3 or 3/4, you cause a vertical compression. K times f of x is a vertical compression of f of x by a factor of k. So it's exactly the same thing as a vertical stretch. It's just that when the number is small, the graph shrinks. When the number is big, the graph grows, stretches. All right, so here's one for you to practice. This is the greatest integer function. I want you to make a table, sketch a graph, and give an equation of 1/4 m of x, where m of x is the greatest integer function. All right, I know several people are still working, but I'm rushing us through a little bit. Okay. So I should be able to jump right to drawing the graph, because now I know the rule, right? When you multiply on the outside by a number, by a small number, it shrinks the graph vertically. And it should shrink the graph by a factor of 1/4. So I'm going to take every y value in the graph, take 1/4 of it, and that'll be my new graph. So x-intercepts, you guys told me, stay the same. So anything on the x-axis stays where it is. Right. Everything else, the y value gets shrunk by 1/4. So at 1, it's going to come down to 1/4. Y values of 2 are going to come down to 1/2, because 1/4 of 2 is 1/2. Y values of -1 are going to become -1/4. Y values of -2 will become -1/2. And y values of -3 are going to become -3/4. So my whole greatest integer function just got whoosh, squished. And we should be able to do that using the table also. Take 1/4 of the y value. M of x is just the y value. So I get 1/4 of -4 is -1, -3/4, -1/2, It's not absolute value, it's greatest integer, right? So it just means round down. So you don't get rid of negatives. Yeah. And then my equation for the pink graph here would be y equals 1/4 times the greatest integer function. Okay, next relative. Still working with multiplication, but this time I'm multiplying inside the parentheses. I'm taking my x value and multiplying it by 2 before I apply the rule f. So previously, I was applying the rule f and then multiplying. Now I'm going to multiply and then apply the rule f. So I'm going to use my original piecewise function, this same f of x I've been using, and I'm going to do f of 2x. So I'm going to plug in my x, multiply by 2, and then apply rule f. So this is going to be f of 2 times -3, which is f of -6. And what is f of -6? Undefined. There is no f of -6. Okay, so now let's do when x is -2, I'm going to end up taking f of -4 because you double the x value before you apply the rule. And f of -4 is 2. When x is -1.5, double the x value, and I'm going to do f of -3, which is 2. F of -2, which is 2. F of 0, which is 2. And now if x is 1, I'm going to apply rule f to 2 because I'm going to double it first. F of 2 is 0. And when x is 1.5, I take f of 3. F of 3 is -1. When x is 2, I evaluate f of 4, which is -2. And when x is 3, I evaluate f of 6. And f of 6 is undefined, right? There is no f of 6. So when I go to my graph, go to x equals 6, I try to go down to the graph. It doesn't live here. Nobody's home. So there's no f of 6. So I plot my points. I'm going to have -3 undefined, so that's not there. -2, 2. -1.5, 2. -1, 2. 0, 2. 1, 0. 1.5, -1. 2, -2. And 3 is undefined. So this is my new graph. This is y equals f of 2x. And the original is just y equals f of x. So how could you describe the transformation that took place if I were to turn f of x into f of 2x? Yeah, it shrunk horizontally, right? And it shrunk all the x values by half, right? So the number I was multiplying by was 2, but it shrunk everything by a half. So it kind of did the opposite of what we expected. You would think that when you multiply by 2, you'd get bigger, but multiplying by 2 actually makes us shrink by a half. So f of 2x is a horizontal compression of f of x by a factor of 1/2. So we were multiplying by 2, we shrunk by a factor of 1/2. So what do you think happens when you multiply by an arbitrary number k? What factor would you shrink by? Yeah, great. So in general, if you're multiplying x by a number k, and that number k is bigger than 1, then f of kx is a horizontal compression of f of x by a factor of 1/k. And you can see what happens is because the domain got cut in half, right? My domain used to go from -4 to 4. Now it goes from -2 to 2. So my domain shrunk by a factor of 1/2. That's my general compression factor. Okay, you try one. This is a piecewise function, brand new piecewise function, p of x. I want you to sketch a graph and give a table of p of 4x. No formula this time because the formula would be 4 different pieces and I don't want you to have to mess around with that. Now that we know the general rule, we can just jump right to drawing the graph if we want to. If you want to start at the table, that's fine. You can always start with the table. But I know that when I multiply on the inside by a number bigger than 1, that's going to shrink my graph horizontally by a factor of, in this case, 1/4. Multiply by 4, it's going to horizontally shrink my graph by a 1/4. So I'm going to take each x coordinate of some important points and multiply it by a quarter. So this point right here is at -8, -3. Take a quarter of the x coordinate. A quarter of -8 would give me -2. So I'm going to move this one into -2. This point right here is at -4, 3. Take a quarter of -4, and we get -1, 3. So you take each point that's important, take a quarter of its x coordinate, and move it that much. So here's an important point at 0, 3. A quarter of 0 is still 0, so this point doesn't move. So when you do horizontal stretch and compressions, y-intercepts stay in the same place. This point at 4, -1, when I take a quarter of 4, I get 1, -1. And then this point is at 8, 6. A quarter of 8 moves it to 2, 6. So this is my new graph. Compressed p of x by a factor of a quarter. And that can get a little tricky. You can kind of forget what you're doing, or the rule can mix you up and confuse you a little bit. In which case, do the table, right? There's nothing wrong with writing out the table. So in this case, I would do p of 4 times -3, right? Just plugging in the x value they gave me. So that's p of -12. I go to my graph and try to evaluate p of -12. Graph doesn't live there. So this one's undefined. Then I try x equals -2. So I do p of -8, because I'm multiplying 4 times the x value they gave me. P of -8 is -3. And when x is -1, plug in there, I get p of -4. P of -4 is 3. And when x is 0, p of 4 times 0 is 0. P of 0 is 3. P of 4 is -1. P of 8 is 6. And when I try to plug in 3, I get P of 12, which is undefined. So then I would go ahead and plot my points. I'd have -2, -3, which is this point right here. -1, 3, which is this point. 0, 3. 1, -1. And 2, 6. So I get all the same points whether I do the table or the graphing method. All right, so our next relative is f of 1/2 x. So again, I'm multiplying inside the parentheses, but this time I'm multiplying by a small number. Instead of 2 or 4 like I just did, I'm going to multiply by a half. Any conjectures about what's going to happen to my function? You guys are not feeling it tonight, huh? So when I multiplied by a big number, my function got skinny, right? It's squished in. When I multiply by a small number, it's going to stretch. It's going to do a horizontal stretch. So let's just go ahead and fill out the table and confirm that that's what happens. Okay, so I'm supposed to take half of the x value I'm given and then apply f. So this is going to be f of 1/2 times -9, which is f of -4.5. What is f of -4.5? Undefined. Function doesn't live there. Okay. Now when x is -8, I'm going to take f of 1/2 times -8, which is f of -4. F of -4 is 2. So this is going to be f of -3.5. What's f of -3.5? 2. F of -3 is 2. F of -2.5 is 2. F of -2 is 2. F of -1.5 is 2. F of -1 is 2. F of -1/2 is 2. F of, when I take half of 0, I still get 0. F of 0 is 2. So now I'm going to do f of 1/2, right? Because I'm multiplying a half times the x value they gave me of 1. What is f of 1/2? 1.5. Okay, and then I'm going to do f of 1. F of 1 is 1. F of 1.5. Here's 1.5. Go up to the graph and go over. What's it look like it's at? 0.5? Yep. F of 2 is 0. F of 2.5 looks like that's -1/2. F of 3 is -1. F of 3.5 looks like -1.5. F of 4 is -2. F of 4.5 is undefined. So I used to, for my function f, the only values I could plug in were from -4 to 4. But now, because I'm going to take half of the x value before I apply the rule f, now I can plug in values from -8 to 8, because I get to half them before I apply the rule. So that's going to make my whole graph longer horizontally. So whoops. There we go. Okay, so I plot all these points, -8, 2, up through 0, 2. And I have 2, 1, 4, 0. 6, -1. And 8, -2. I accidentally deleted it. So now my graph looks like this. So I took my original graph and I grabbed the two ends of it and pulled it horizontally, stretched it. And how much bigger is it than it was? It's twice as big. So I was multiplying x by a half, and my graph got twice as big. So f of 1/2 x is a horizontal stretch of f of x by a factor of 2. So what do you think the stretch factor is when you multiply by a typical number k, generic number k? It's less than 1. Like, let's say it was a third. What do you think your stretch factor would be if you multiplied x by 3? Yeah. So it's the reciprocal. It's the reciprocal, which is 1/k. Or you can just write the reciprocal of k. So f of kx for small k's is a horizontal stretch of f of x by a factor of 1/k. That is the reciprocal of k. So the reciprocal of a half is 2. 1/1/2 is also 2. All right, we'll skip the practice. We now know how to do the missing 4 transformations. You can fill those in on your own time. And with the 5 minutes we have left, 3 minutes we have left, see if you can do this little matching activity. This is the original function f. Match the equations to their graphs.